First talk will be analysis and improvement of entropy estimators in NIST SP 890B for non-IID entropy sources. And the talk is a paper by Chu Yang. I hope I'm not mispronouncing that.
It's okay.
Okay, Mai Wan, Chan Tianyu, Lin Jingzhuang, and Jin Jiyu. And
okay, thank you for the introduction of the section chair part. Okay, my name is Zhu Shuangyi from Institute of Information Engineering. I'm very glad to be here to give a speech on my paper, and my talk will be divided into 3 parts. First is the background, including introductions of the main topic and the NIID certification. And then is our contributions, and finally is a short conclusion. As we all know, random numbers are essential cryptographic applications. For example, the key generation, initialization vectors, nonce, and so on. An entropy source generates true random numbers on the basis of some physical phenomena, and entropy is employed to assess and quantify the quality of the randomness. But there are many types of entropy, while the main entropy is used in the NIID certification. It corresponds to the difficulty of guessing the most likely output of the entropy source. Well, how to estimate the entropy of an entropy source? In AIS31, developed by the German BSI, the TRNG designers are required to provide a stochastic model for the entropy source, and so the entropy can be estimated by the stochastic model in theory. But in NIST NIID, designers only need to make sure their entropy source can pass a set of statistical tests, and we studied the statistical tests in NIID. Here is a brief introduction of the versions of NIID, because when we started the NIID, there is only the second draft version, while the standard version is published in January this year. Luckily, the problem we have found in the old version is still existing in the current version. So my speech is somehow still meaningful. Thank you. Here is the test procedure. First, we need to collect data and then determine the track. That is to check whether the data are IID or not IID. We focus on the non-IID track. Because in the IID track, the entropy is easy to estimate. Only one simple estimator is used to estimate the mean entropy of entropy source. But in non-IID track, 10 estimators are employed to estimate the mean entropy. Finally, the minimum one among the 10 estimates is selected as the mean entropy of the entropy source. For these are 10 estimators in NIID. We divided them into 3 types: the basic type, the statistic-based type, and prediction-based type. We found that NIID often underestimates the entropy source in the non-IID track. We indicate the impact of underestimation, and we point out the reason. The collision estimate and the compression estimate in NIID are flawed, and experiments results support our conclusion. Well, we all know that for only one estimator, underestimation is less harmful than overestimation. But for the test suite, the underestimation of an estimator is more harmful than overestimation. Because in NIID, every estimator calculates its own estimation independently. So at the minimum, estimation of all is selected as the final result. That is to say, most overestimated values are not reflected in the final result. However, if an estimator provides a significant underestimation, the final result will be assigned to this underestimated value, no matter how correct the other estimators are. Now I introduce I give an introduction of the collision estimate. The collision estimator focuses on the collisions in the tested sequence. If any value of the sequence repeats, we call there exists a collision. This estimator calculates the mean number of samples to the first collision as a statistic. I provide a simple example. In this simple sequence, we can see two collisions, 1241 and 324113, and the collision statistic is 4.5. The whole flow path is data, statistic, and mean chopping. Here is a problem. For non-ID track, this estimator calculates the mean chopping on the basis of a statistic calculated from non-ID data. However, the formula G used to calculate the mean chopping is derived from hypothesis that the tested data are IID. That is to say, G is unsuitable for non-ID data. And we provide a simple example to show how the collision estimate underestimates the mean chopping. According to the current version of NIST, this estimator is only applied to binary inputs. So, if the tested data obey a first-order Markov process of 0, 1, whose transfer matrix is this, we can say that when P is larger than 0.5, the collision estimator will underestimate. And when P is less than 0.5, it will overestimate the mean chopping. We can say in NIST, the collision statistic X bar obeys the following equation. It is a complicated equation, but it's not suitable for this simple process. In fact, the true relationship between X bar and P is just X bar is equal to 3 minus P. This figure shows the big difference between the collision estimate and the correct theoretical mean chopping. You can see in the left part, the collision estimate is significantly lower than the correct theoretical mean chopping. But in the right part, the collision estimates are all 1, which is the max value of the mean chopping. And we test an entropy source based on the first order Markov process. The data size of each group is 1 billion. And they, of course, they have different transfer probabilities. And we draw a picture to show this data intuitively. We can see that the first 3 estimators provide overestimates, and the number 4 to number 9 estimators provide similar estimates with the theoretical mean chopping, and the compression estimate and collision estimates have a evident reduction. This is consistent with our conclusion. We also found that the collision estimate is designed under the ID assumption, but for ID track, it also can underestimate the mean chopping because it is highly sensitive to the statistic when the entropy source are perfectly random. And in addition, it takes the 99% confidence intervals lower bound of x bar to calculate the mean entropy, which means a value slightly smaller than x bar is calculated to estimate the mean entropy. And this causes a significant reduction of the mean entropy. We can see this phenomenon in the yellow rectangle. You can see that the coefficient estimate is very sensitive to the statistic. A small reduction of statistic will cause a huge reduction of the mean entropy. And this is the experiment's results. You can see that the coefficient estimate is under 0.9. And here is the compression estimate. In fact, the compression estimate has the same problem with the coefficient estimate, except for these results. But in fact, this abnormal results comes from the inaccurate standard deviation in the compression estimate in the second draft, and now it is fixed. But the other problems still exist. And we suppose that these flawed estimators, the existence of these flawed estimators is due to the following reason. The NIID only gives a formula of mean entropy for independent random variable x. And every estimator in NIID is trying to calculate something like max pi to get the mean entropy. To avoid this problem, we propose an estimator directly according to the mean entropy of the high-order Markov process, because this is a very common model for non-IID entropy sources in the real world. And instead of calculating something like max pi, we directly estimate these conditional probabilities. So our estimator is very suitable for high-order Markov process. We also do comparison with NTB estimators. The Markov estimate in NTB is specific to the Markov process. However, it is only suitable for the first order Markov model due to the heavy computation complexity. And the prediction-based estimators in NTB are newly proposed in CHAS 2015. Our estimator is a basic frequency-based estimator, but has comparable performance with the prediction-based estimators. And we do experiments, and we can see that the estimate provided by our estimator is close to the correct estimate. And the highest estimate of the NIID is much larger than the correct estimate. And the lowest, that is the final result of the NIID, may be lower than the correct estimate. And the best estimate, which means is closest to the correct estimate in NIID, are all provided by the prediction-based estimators. So here is a short conclusion. Accurate entropy estimation is critical for evaluation of RNG security. We prove that the collision estimate and compression estimate could provide significant underestimations for non-IID data. And we propose a new estimator to calculate the mean entropy of non-IID sources on the basis of conditional probability. And experiments show that our estimator provides those estimates to prediction-based estimators in NIID. And that's all. Thank you. More details are in favor.
Any questions? John.
Yeah. First, thank you very much for this. This is really nice work. I was happy to see that it worked even with the change in 90B for where we changed to only do this for binary. I was glad that your result kind of held up. I wanted to ask, have you considered how with your new formula where you're doing an estimate based on a Markov model, have you considered how that would work with other IID sources, or other non-IID sources, or even IID sources? So how does that work if you have a source that's not Markov, it doesn't follow a Markov model? Do you still get this big underestimate because it's an inappropriate model?
Well, it's a good question. In fact, the very, very simple formula is only used to show that the collision estimate is not suitable for the non-IID source. And of course, there are so many different non-IID models, and in fact, so I think the existing prediction-based estimators we can add many different estimators in this type of estimators. So if we find some specific non-IID models, we can just add this predictor into this type of estimators.
All right, thank you very much.
Any other question? Have you contacted NIST for modify it in the future versions?
Somebody from NIST might have heard this.
I haven't contacted, and I want to contact NIST.
Yeah, any other question? If there are no other questions, thanks, speaker again. Let's immediately go on with the second talk.